So let's see, last time we finished that handout from before. Where are you? There you are. So that was that confidence interval one. We had one side about 8.1, the other side about 8.3. Does anybody still need that? Confidence intervals. Let me find some more of those. Hey, all right. No, that's one that's already written on. Should I have more? So no, but you can have this one. That would be nice for you. Got one side written on. Look at that. Should have more of those. Okay. No, okay. All right, guys, so. Guys, so last time we started with the idea that led us to this. We kind of restarted it and then put stuff in there that related to percentages. So like a binomial situation, NPQ stuff. So we could build a formula that would allow us to figure out a confidence interval for percentages. And this is related to the thing you always see when there's an election coming up. You always see somewhere 40% want to vote for candidate A, 42% want to vote for candidate B, and at the bottom it says plus or minus so many percentage points, right? And they don't just make it up. Kind of seems like we're not really sure if we're right. Let's just say plus or minus 4. They actually calculate it. So ones we did last time, if you were here, we had relatively small samples. So our plus or minus came out to be 8%, 10%, larger. But when you see polls on the TV or you see them online, they're normally talking about data from thousands of people. So that's why the larger n is, the smaller that error is going to get. The more sure you are about what you see, so the less far out you have to go to be so confident. Right? So that's the one we talked about before. We developed this formula now. Somebody who was here, remind me, what does that hat mean on that P?
Sample.
Good, it comes from a sample. So P is population percentage. P hat is just sample percentage. The same way that mu is the population mean and X bar is the sample mean. I like it. But even if they're wearing hats, what are P hat and Q hat? What do they do when you add them together? They still have to make 100% or 1. I like it. Kick ass. So no matter what clothing they put on the P and the Q, they still have to add to be 1. There's still the same idea about failure and success. They're just talking about a sample now. So let's do a really quick sample problem using this, and then I want to get into the new stuff today for the T-score stuff. Let's say we sample 47 correspondence students. And 11 of them say they like parking here. Like the parking. So find the, let's do 90% confidence interval for the true percentage, population percentage, who like parking here. Just going to do this problem. Percentage problems always feels like they don't give you enough information because they don't have to give you a lot of information. What is the percentage that we can create from the sample here? Say again?
11 divided by 47.
Yeah, 11 out of 47. 11 people we talked to out of 47 total people did something. They liked the parking here, right? So that's going to be what? Not what is it, but what symbol does it kind of go in for? Yeah, I like it. And then what is 11 divided by 47? 2, 3, 4? Neato, I like it. So these guys, P hat and Q hat, you take those out at least 3 places. So early in the semester I said if you just round everything to 4 places, you'll be covered. So if you want to do that for everything, that's beautiful. I have no problem. Standard deviation at least 3 places. P hat, Q hat at least 3 places. Percentages that come off the chart, 4 places, because there are 4 places on there. All right. So what's Q hat got to be? I like it. Now be a little more specific. 7, 6, 6. I like it. And of course, what's N? N is 47. I like it. Now, if you missed last time, you also missed something changing. We're not talking about means anymore. So I cannot use central limit theorem here directly. So n greater than 30 is no longer good enough. So I actually have to check to make sure it's normal. We discussed this last time. It really, really, really just makes too much sense. If the mean is too small, it starts off tall and goes down. Does that look normal? No. If the mean is too big, it runs up against the maximum. It goes small to big. There's no room for it to be normal. So I have to put it in the middle somehow. Right? So the mean's got to be big enough. But also it's got to be, the other side's got to be not too close to the wall over there. So if I have 47 people, right? What's the least number of people that get it to 0? What's the most? 47. So if the mean was 47, that would be just a big tall one at the end. There's no way it could go up and come back down again. All right, so I discussed that last time a little more in depth. So I'm going to say here, this is the check, not n greater than 30. That works for means. That's the central limit theorem, which talks about means. Can't use that same thing here. This has got to be what's true. Is that true here? Who remembers the shortcut? What is NP? In fact, this will be NP hat, right? We don't know what P and Q are. What is NP hat? You know it from the beginning. The minute I wrote that second part of that. What is? Say again? What is it? What's the number? 11. 11. How did I construct P hat? 11 divided by n. So what is n times P hat? Freaking 11. Please let that make sense. If you don't like that, then do this. Do 47 times 0.234. Do it. What's 47 times 0.234? I'm hoping to God some of you guys realize, why do that? That's dumb. The 47s cancel. 47 times 11 out of 47 is 11. But just in case, what is 47 times 0.234? Yeah, freaking 10.998. Freaking 11. That is at least 5, right? It's bigger than or equal to 5. Cool. And what about NQ hat? So that would be 47 times 0.766. That is going to be 36.002. Is that true?
Mm-hmm. Yeah.
How did I know that? Because I got to add up the freaking 47. So some of you guys are just going to go, oh, that's NP hat right there. That's the number of successes I see. And how many failures do I see? 36, the rest of them. Or you can just calculate. That's fine. It'll get you the same answer. They have to be at least 5 for this to be normal enough. Just like checking to make sure the n is greater than 30. It's the same idea. It's just not the same situation. So that's why it's different. Okay, now do I have enough information to use my formula, this one? What's p hat? 0.234. That's my best guess. That's what I see in the sample. If somebody told me, just give me one number guess, it would be 23.4%. It's my best guess. We're going to improve on that guess a little bit by making a little interval around it. What's the z-score going to be?
1.615.
Yeah, z is 1.645. You could look up on a little baby chart. We're going to see today how the t-score chart gives me z-scores and how to use that. So this will be 1.645 square root 0.234, 0.766, p hat, q hat, all over n, 47. So you guys try to do that there. Get that error for me. If you need to borrow calculators, always just come up here. Bring with you a ID or keys or 0.102. Sounds like where it should be. Yeah. So 0.234, give or take 0.102. I like it. Make sure it turns on. All right, now what do you do? Make sure it turns on. Yeah, now you do what it says. 0.234 minus this. What's 0.234 minus this? 132. 0.234 plus this.
0.336.
All right. So that's the interval. Make sure it turns on. All right. And then the best part of this whole thing is writing a paragraph at the end, a little sentence actually, that describes what the heck we just found. This is the interval. This is the confidence interval. Well, how do I capture what that means? We are 90% confident that the interval 13.2% to 33.6% contains what?
The true percentage.
True percentage of,
People who are pregnant.
I like it. Contains a true percentage of gross 1 students who like parking here. Would you say that's a very wide interval? Just your gut? Do you think that's a wide interval? From 13 to 33%?
Yes.
Yes, I'd say so. If the doctor said to you, you've got a somewhere between 13 and 33% chance of coming out of the surgery. Both of those sound sucky, but my God, that's a huge range. It's not quite as bad as, 10 to 90% chance, but still. It's a pretty wide interval, which the main purpose of doing this captures how certain we are in general. If I just say I think it's 23.4%, it doesn't give me any idea about how certain I am about this. This tells me, I'm not really that certain. And what part of this would contribute to me not being that certain? Why would I not be very certain about what I found? Where did I get it from? Only what? How would I make myself more sure about what I calculate? What would I do with my sample? I'd probably make it big. Is this a very big sample? 47? No. So that's why this came out so wide, because I had such a small sample. I'm not going to be that sure about what I see. So the confidence interval gives us an idea about how sure we are about what we found. All right, is that decent, guys? With me. So somebody said, yeah, this has got, like a 20% to 60% success rate. You're like, so you have no freaking clue. But if they said, yeah, it's got like a 55 to 60% success, oh, you're like, oh shit, you got a lot of data. You know what you're talking about. Do you guys see what I'm saying? It's not exactly right. It's not. They can't tell you this exact number because you can never do that in life. But they can at least communicate to you how sure they are about what they're talking about. All right. So that's what we did last time. And then we just barely started getting into something that's even closer to how things work in general. There's still a piece of the this formula that doesn't really capture what happens normally. There are situations where we know this. We have a population and we're talking about a subgroup of that population. So we know the population standard deviation, we just don't know the mean of that subgroup. So I can have a situation where I don't know the mean, but I do know the standard deviation of everybody. But what happens normally is we go into a situation, we know shit. We take a sample, we get X bar, we get S. We have no clue what mu is. We have no clue what sigma is. So we got to talk about what do we do in that situation. That situation sucks. So just to cut to the chase a little bit, the thing that we do is when I don't know this, when I have to use this as an approximation, I have to use S because I don't know sigma. So I have to use S as an approximation. We're no longer allowed to use the z-scores. We're no longer allowed to use that normal distribution. We have to use what's called the t-score distribution, or what's known as the student's t distribution. Right? And the whole idea behind the name was because this guy that worked at Guinness, anybody drink any Guinness? Guinness got me through my physics today. Huh?
Craft here.
Yeah, I know. This is true. But you can even go beyond that. Not here? No?
Dry
They,
IPAs only.
I see. So they kill you on site, or you will. So I'm not going to drink Guinness anywhere near you. I got that set. All right, I want to live a little longer. So he worked at Guinness, and he was doing some data analysis, and he created the idea of this T distribution. But he could, if he said his name when he submitted it, the company would know he submitted it, and they were supposed to have intellectual property rights. They're supposed to be able to keep those for themselves. So he submitted it as under pseudonym, anonymously. He just said his name is Student. So that's what it's known as now. Even though we know it's William Gossett, we didn't change the name. I don't know why we're still protecting him. He's long dead. And his employers are also. But all that is just a side note. It's kind of nice. The history sometimes of some mathematical stuff is interesting. There's deaths and murders and poisonings and duels and people going insane. It's really nifty. There's also, people just being normal. But the thing with this T, the main idea of this T-score, its main job is when I don't know sigma, when I only know S, a T-score will always be bigger than the Z-score I would have used. So if there's something I don't know, something I'm not sure about in my sample or just in general, my interval should get bigger to cover me for that fact, right? Do you guys agree or no? So like the thing, I don't like fish. I don't like to fish. I don't like any of that shit, but I just love this idea. I throw a fishing net out, and there's a certain kind of fish I want to catch, and I know he's somewhere around here. I know he swims about this far, but I'm not really sure. So I'm not going to throw a net out this far, this big. I'm going to throw a little bit further because I'm not really sure how far this way and that way he goes. You guys kind of with me? And I know how fish work. Don't come at me with, I think fish could probably do, it's just a nice little analogy, all right? So I throw a little bit bigger net to cover for the fact that I'm not sure how big of how far he goes. You guys with me? Or she. I'm not getting into the biology of this big fish. Right. So let's look at this. For a 90% confidence interval, we just figured out that the t-score, the z-score we just used was 1.645, right? Now, the t-score's job is to cover our ass from when we don't know sigma, when we only know s. The t-score was invented to use when we only know s. You guys with me? This is important. That's why I just said it twice and slowly. Okay? Because everybody always gets confused about when do I use a t-score. The formula freaking tells you. When to use a z-score? When I know sigma. So when do I use a t-score? When I know s. Okay, there you go. Now they both have to require also that it's normal. The population they're coming from has to be normally distributed. So let me ask you this. If a t-score covers my ass for not being sure about the standard deviation, I'm using an estimate if I'm using s. Is that decent? If I took a sample of gross month students, will their standard deviation be the same as the population standard deviation? No, it's not. The bigger my sample gets, what should happen? Should s be better or worse compared to sigma? As I let my sample get bigger and bigger and I pick randomly. Should s get better, closer to sigma, or should s get further away from sigma if I have a bigger and bigger randomly selected sample? If I get a bigger and bigger randomly selected sample, should I be more sure about what I find or less sure about what I find? Say it again. I'm hearing some lesses, and that's making me concerned. If I take a large frickin' sample, randomly selected, compared to a small one, of course I'm going to be more sure about the large one. Is that cool? If I take 2 gross month students and find their average age, I don't feel very good that that's the average age of all gross month students. Is it possible I got lucky and it is? Sure. How do I feel about it? Not good. All right. So the bigger the sample gets, the smaller the t-score can get, because the reason we need it is less and less now. The more sure I am about this approximating that, the less I need t to be covering me for that. So the bigger my sample gets, the smaller my t-score can get. Until it becomes the same as what the z-score is, because then it's not needed at all. I don't need to make it any bigger. So if I took a huge-ass sample, I don't need to use t-scores at all. I could just use z-scores, because I feel really good about my standard deviation. Should be really close to the actual population standard deviation. Are you guys with me? Okay, yes, ma'am?
How would you know what is considered a large?
That's beautiful. If you look at that t-score chart I passed out, I love the fact that they just use the word large. Why? Because it depends on the situation. It depends on the situation. Okay, so let's look at a few examples. So whatever the t-score would be, if I had to use a t-score, it's going to be bigger than 1.645 for this. So let me do a few more pieces before we can really use this chart. They don't have sample size on there. They have something called degrees of freedom. You can't take away my degrees of freedom. What the shit is that? All right. So let's say I had a sample of 5 test grades. So stay with me now. I'm going to show you why it's called this. And then I'm going to show you how it relates to something we did earlier this semester. Let's say I have 5 test grades. Stay with me. 5 test grades that average to be 80. You with me? 5 test grades, average to be 80. Can any of you tell me what any of the test grades are? Could one of the test grades be a 2? Of course it can. Right? Because I don't know how much extra credit was given. Could one of the test grades be 120? Sure, I don't know. Maybe there's a ton of extra credit on this thing, right? Or maybe it's out of 150 points. I don't know. All right. So I have no idea what any of the grades are. Can somebody tell me what all the grades add to be? They don't add to be 80 because then they're average would be much less than 80. They're supposed to average to 80. How do you find the average? What do? Add them up. In this case, divided by 5. So when you add them up, what should you get? What do you divide by 5 to get 80? What should this be so that this is true? Guess what? This is freaking algebra. Again, algebra. Huh? I'm asking you, what is that number? You've got to tell me. Now, some of you guys are like, you just said a minute ago that we don't have a freaking clue what any of the test grades are. That is true. But I know their average is 80. 400, yes. What do I divide by 5 to get 80? 400. 5 times 80 is 400. So if you know an average of so many things, you don't know what those things are, but you know what they add up to be. You guys understand that? That's a very basic idea of averaging. Do you guys get what I'm saying? This is nothing connected to this course. This is just a truth, right? So if I have 3 things that average to be 60, what do those 3 things add up to be? 180, because 180 divided by 3 is 60. That's the only way to have an average of 60 is the sum divided by, in this case, 3 is 60. That's how you find the average. All right, you guys are looking like it's magic. Okay, we're going to keep going. So, if I just start making up test grades, the very first statement I made seems to say I can do that. Because I don't know what any of the grades are. But there is a point where I have to stop just making shit up, and I gotta actually make it come out to be right. So we just set up they have to add to be 400, right? So say the first test grade, let me say it's a suck ass to 27, and the next grade is 119, and then another grade is 80, and another grade. So I'm just making them up, right? And then another grade is I don't know, 35. Well, now, if I make up one more grade, that'll be 5. I can't make up that last grade, right? It's got to be the thing that makes them average to be 80. Or more specifically, the thing that makes them add to be 400. So what does that have to be? Do it in? Yeah, because what do? You add these up, and what do you get? 261. And I need to get 400, so it's got to be 139. So how many total grades? What was the sample size? What's n here? 5. How much freedom did I have? How many of those could I just make shit up for? Didn't really tell you the answer, but I sort of did. How many of those did I make things up? How many of them did I just make up? 4 of them. Not all 5, because then if I just make up 5 numbers, are they going to average to 80 for sure? No. Right? 1, 2, 3, 4, 5. That doesn't average up to be 80. Shit. So that I'm always going to have one less degree of freedom. How much freedom did I have up here? 4 things I had freedom with. The last one, I had to make the mean work. So that's why we call it degrees of freedom. And that's why it's related. That's why it's n minus 1. Do you guys remember earlier in the semester when we did standard deviation? We divided the population 1 by n, but we divided the sample 1 by n minus freaking 1. So that's connected. Holy shit. Okay. What? All right. So let's take a look at this. Everybody's got a T-score chart? Everybody sneak in. I get one of those. T-score chart. Everybody's got a T-score chart. Okay. A few minutes from now, I'm going to have somebody say, I need one of those. Oh, I love you. This is going to be awesome. There you go. Yes, cool. Right. So here I've got this, while this guy wakes up. Here I've got the z-score I would use. I know the t-score's got to be bigger. Let that make total sense. What's the t-score's job? Is to cover my ass for not knowing the real standard deviation. So it makes sense it's going to be bigger than any z-score I would use otherwise. Does that make sense by itself? The size of it depends on how big my sample is. Because the smaller my sample, the more important it gets. It's got to like really cover my ass when my sample gets smaller. So say I have a sample of size 11. I know it's normal. What would the t-score be? Well, let's take a look. So first thing is, and let's say so it's a 90% confidence interval. You're not going to completely understand why this is so right now, but in the next chapter you're going to totally love the two top rows. How many tails do I make when I make a confidence interval? How many tails do I make? 2. Does that make sense? If I have a normal distribution and you draw in a confidence interval, there's 2 tails, aren't there? So in the next chapter, we're going to be testing a claim like, I think it's greater than this. Well, that would be 1 tail because I just care about up. Confidence intervals always make 2 tails. So which row am I going to look at? The second one, because it says 2 tails. Do you see that? Okay. So confidence intervals, I could look at that one. To be honest, you could use either one depending on the way you look at it. But if I want a 90% confidence interval, what area is out in the 2 tails? 90% in, 10% out. So I'm going to look at... Boop. So that is the same thing as a 90% confidence interval. Because that would leave 10% outside. That's what that means. I like it. That's all. Nothing major. And that's how we've been doing confidence intervals from the beginning. We started with, well, what's outside? That's all this means is, what's outside? 90%, 10% outside. What's my degrees of freedom? N is 11. So the degrees of freedom is 10. It's amazing. Because what's degrees of freedom? N minus 1. So look at 10. Look at point 10. Look at 10% over here. So what's my t-score going to be? 1.812. Does that do like I said it should do? It is bigger than the z-score would have been. I'm going to make you guys do something similar to this in a minute. I got a little handout. You know me, right? I should probably turn you around. So what if n was, let's make it like 28. What if n is 28 instead? And it's normal. What would the t-score be? Same situation, 90% confidence interval. Yeah, the degrees of freedom now would be 20. It's always n minus 1. 27. 27 degrees of freedom. I'm still in the 90% one, the 10% outside here. So if we go down here, I get 1.703. My sample got a little bigger. What did my t-score do in response? What did I say, 1.703? My sample got a little bit bigger, which means I'm a little more certain about my S being closer to sigma. So my t-score, what did it do? It got a little smaller. It doesn't have to cover my ass as much because I'm a little more sure about what I saw because I took a bigger sample. So it kind of makes sense. The smallest this could get is what the z-score would have been. Right? Because t-scores are always going to be a little bigger than z-scores unless they're not needed, in which case I'd use this guy. And look at the very bottom of this row here. The very bottom of this 90% confidence interval, what do you see? The freaking z-score, right? And what size sample is that for? Large. I love that shit. So, I mean, officially, if you wanted to, you can consider large to be greater than 2,000, because that's what it makes it look like here, right? I like it. But I want you to realize if it was absolutely critical that you got it precise, you would be using t-scores more than just 3 decimal places. And then large could be in the 10,000s. But for us, if I'm only concerned about 3 decimal places, large is above 2,000. That's good to 3 decimal places. So it has to do with the rounding on this chart as to, what large is.
Somebody said really good gaps in between them.
Where? Tell me, for example.
Like between 40 and 45.
Yeah, so why is that? Why is that? Why do I have to go by 1 up here? Because look how much this is changing. This changed by 0.2, this changed by 0.13. But look how, isn't it changing less and less and less? It's slowing down how much it's changing. Until I get to the point where I'm like, why keep going by 1s? Let's start going by 5s. Because look how little that changed from 40 to 45. I mean, look from 38 to 39. How much did it change by? 0.001. And then, so the chart's like, all right, I only have so much freaking room. Let's start going by 5s. And then it's like, let's start going by 10s. And then it's like, let's go by 100s. And then it's like, let's go by 1,000. Because it stops changing so fast.
If you're in the 73, what would you use?
Oh, I love it. So for us, since you have this weird-ass teacher that wants you to learn shit, doesn't let you use much technology, you just always go down to be more conservative, right? So if you got 73, you go to 70. Now, if it was like degrees of freedom 79 and you use the one for 80, I'm not going to take points off, it's fine. But if you're in the middle, you always round down, so you're more conservative. Anything that you're not sure about, you should always make the score bigger to cover you for that. So that's why you go down. All right, maybe. So t-scores, when do I use them? When I don't know sigma. When I only have S. Now that's one thing. Also, you need to have a normal distribution. If I don't have a normal distribution, I don't care what I know or don't know. I can't use shit. I can't use anything. So if the problem doesn't say it's normal, what's got to happen that tells me it's approximately normal? Notice I'm back to means, right? So what tells me it's approximately normal as long as the sample size is bigger than 30, right? I love it. We're back to means, so it's just greater than 30. Percentages are the ones that are like NP hat and Q hat. I got to look at both of those. Okay, all right. Nothing changes here. We just keep using it in different ways. Okay, so let me give you this. I think we have enough information now, possibly. Let's find out.